Yeah. All right, so yeah, we do not know how bad it is. Okay, we do not know how bad it is. Yeah, we want to see another different way to solve the same problem first. All right, yeah. Next thing we need to do, find the performance number of this algorithm. So what's the performance number? Yeah, here, this concept is not that clear. Oh, do you feel the light this way? Yeah, compare to dark. How about feel okay this way? This way?
I'm good with either.
Good with
I
you.
still vote dark, but
Oh, you know.
My eyes are better.
All right. Yeah. This way. Okay, let's try this way. All right. Yeah. All right. Nope. Yeah. So now that something called a performance number, there is no clear definition here, but we want to compare. We want to use a number, certain number, to describe a fair performance measure. That's something we like to do, some fair performance measure. Here we have addition. We also have multiplications. Can you compare additions with multiplications? Compare apple with pear or different things, right? Yeah.
Yeah.
Different objects. You need to compare different objects here. Can we do some conversion between two different objects? You know, use some equation, some.
Yeah, because
All right. Yeah, we need to do that. Yeah, otherwise, how do you compare? One side 100 additions, the other side 45 multiplications. Which one faster? How do you know? Right? Think about that. So we need to find some equalities between those two different operations. Yeah. All right. Oh, yeah, I do not go back. Yeah. So let's do that first. Let's add some assumptions. We need a little more assumptions here. Okay. Yeah. So it is allowed to add a reasonable assumptions. And our assumptions should be very close to the real world cases, real world situation, our assumptions. Yeah. Here. And our added assumptions should not alter the problem difficulty significantly. We do not change the problem difficulty level. Same difficulty level. Okay? Yeah. 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 All right, so here, this is our assumption. We know multiplication is slower. Yeah, I need to admit that side. Because if I do this side, my remote control is disabled. So that side. All right. So here, everyone of you here know multiplication is much slower than addition in general in computer. So here, not you do multiplication. When computer does a multiplication, it is much slower than addition. But how much slower? We need to know that. How much slower? That ratio here. For addition, because it's faster, so we assume the amount of time for one addition is 1 unit of time. Just 1 unit. Okay, yeah. Here, this unit, certain number of nanoseconds. because right now our computer is very fast. So a certain number of nanoseconds, that level, you know nanoseconds, how fast, nanoseconds, how big, nanosecond. 1 nanosecond equals 10 to the negative 9th power of s second. Oh, 1 billionth of a second. 1 billionth of a second. That's 1 nanosecond. Yeah. Okay, yeah. So that's how fast our addition could be. All right. Then for multiplication, it takes 10 units of time. The ratio is 10 to 1 ratio. Not precise, but close. Here in our discussion, we make this assumption. This assumption is pretty close to the real world situation, cases. Okay, yeah, 10 to 1 ratio. Now we can compare multiplication and additions, right? 100 additions, you need pretty much the same amount of time as 10 multiplications. Okay, all right. Yeah. So now, with this assumption, we do not change the difficulty of this problem. So we should be fine. Yeah. All right. So let's do the work. Now we can count the number of additions, then we count the number of multiplications. At the end, we can calculate the number of units we need. How about that? The total number of time units we need to calculate this polynomial. Okay, all right. First, how many additions do we need? Look at this polynomial. Can you tell me the number of additions we need to do in this polynomial? How many?
Maybe n plus.
It's just n, right? Is you have two,
Oh,
same
yeah.
as before,
No,
like
it's
you have
n.
two factors, one multiplication.
Good.
So,
N. The answer is N. Okay. All right. Yeah. Yeah. All right. But here, when you do the counting, yeah. Because here we also have the dot, dot, dot. When we have dot, dot, dot thing, we have the keep tracking problem. How do you keep track of all the terms with dot, dot, dot? Okay, yeah. Here, when we count the number of additions, one addition corresponds to one plus sign, right? One plus sign. So we only need to calculate the total number of plus signs. Okay, but the question is, how do you keep track of all the plus signs? With the dot, 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 how do you keep track of all the plus signs? Okay, yeah. So here, a better method, try to find some suitable reference. Because plus sign, there is no reference. All the plus signs look the same. You cannot tell difference. But can you associate the first plus sign with the subscript of A1, the second plus sign associated with the subscript of the second term A2, and so on? Can you associate the last plus sign with the subscript of the last coefficient A sub m? One-to-one correspondence, right? That's one-to-one correspondence. For the plus sign, it's hard to keep track of them because they all look the same. How do you tell the difference? Hard to keep track of. But for the subscripts, is it easy to keep track of all the subscripts? They're natural numbers, all right? Counting from 1 through n, that's n. How about that? Here, this counting method, I call it counting by reference. When you do the counting, you need to find appropriate reference. All right. So here, let me describe this method. Yeah, because later we will use this method many times, counting by reference. Okay, counting technique. This counting by reference technique. Okay. All right. Essence of this method. We need to discover one-to-one correspondence between two mathematical objects. Yeah, two objects. Okay, one-to-one correspondence. Here, in this example, we have these two objects. Object one, object two. Object one, addition. Object two, subscript. Think about that. Object one, additions, plus signs, hard to count. Hard to count. Hard to keep track of them. Okay? But object two, easier to count. Easier to keep track of them. Okay? Yeah. We just switch. When we need to count number of object one, we just switch to counting number of object two. After we get the answer, that's the same number for counting number of object one. How about that? Okay, so this simple method, right? Yeah. So the answer, n units of time, n additions, n units of time. Part one, addition part. Part two, multiplication part. Okay, all right. B.2, all right, so yeah, let you see a little bit. Okay, yeah. Then we need to move to the next topic. Okay. Yeah. All right, B.2, second topic. Estimated cost, total cost. What do you mean cost? Cost here, we mean the number of time units. That's the cost. We treat that because we need to pay that amount of time. So not money, but time. We know time is, precious. No. So that's the cost. Okay, yeah. All right. So let's work on the second part. We need to count the number of multiplications. We did part of it in the first half. Remember the general term, the representative, we count the number of multiplications for the general term. Yeah, that's k multiplications. But here we need to add up multiplications from all the terms. Okay, let's do the work. Yeah. All right. Yeah, because this part we already did it. All right. Yeah, we already did it. The answer is k. We did it. Okay. So then accumulate, add up all the number of multiplications, 1 plus 2 through n. You know this formula, right? Yeah. Simple formula. Okay, that's the formula. This many multiplications. To calculate this polynomial, we need this many multiplications. Okay, but we need to convert it to the number of units, time units. Then we can add the addition part, total number of units. All right, so that's calculated total units. Addition part, 1 times n, right? Yeah, each addition corresponds to 1 unit, so 1 times n. But for the multiplication, we need to use 10. Remember our assumption 10, each multiplication equals 10 units of time, 10 times that 1/2, so you have this 5. 5n times n plus 1. Okay, so the final expression, this many units, 5n squared plus 6n, total number of time units we need to calculate this polynomial. That's the number, concrete number we can use for comparison. first part. Okay, all right. Yeah. So we know how fast or how slow this method is, but we do not have another method. We need to consider another different way to evaluate a polynomial. Then we can do comparison. So next, we need to consider a different method. Okay? Yeah. But when we consider the different method, we want to do better, right? You don't want to do worse. You want to use less time than this number here. You want to use fewer number of time units than you have here. Okay? So we need to reduce the number of units, time units. So our goal, reduce the number of time units to do the same thing. Okay? Yeah. Improvement strategy. Now we need to improvement. So what strategy should we take? Improvement strategy. Strategy, every time when we need to do something new, we may need some strategy. If it's non-trivial, if it is relatively hard, we need some strategy. Yeah, so here, the strategy, let's do observation. Now we need to do analysis, observation for some property. All right, look at the cost ratio. Cost ratio for multiplication and addition. The numerator here, unit cost for multiplication. The subscript m means multiplication cost. Single multiplication cost. Okay? Over single addition cost. That's 10-to-1 ratio. Okay? That number is pretty big, pretty significant, right? 10-to-1 ratio. Quite significant difference. Okay? All right. Now, when you have certain amount of investment, suppose, because when you need to improve, you need to put your resource, right? Think about it. Put your resource, put your investment, invest your time, invest your, probably, your resource. Okay? Yeah. When you have freedom to choose where to allocate your resource, which part you want to apply your resource, on multiplication or addition? Think about this question. You have two different places to apply your precious resource. One is multiplication reduction. Another place is addition reduction. Which way you feel better? Yes, multiplication. Yeah, look at the, shares contribution in the total amount of time units. Multiplication share is this much bigger than the percentage of the addition. When you put investment on the multiplication part, you have more room to reduce the time units, right? The improvement room is bigger. And the percentage for the addition, very little. You do not have much room to do the improvement. Think about that. The room is very little. Even if you spend a lot of resource, but the rewarding is very little. Okay? But multiplication, that chunk is so big, you have much bigger room, bigger chances to reduce that big number. How about that? Think about that. So our improvement strategy, we try to reduce the number of multiplications, not additions. additions because that percentage is so little. Rewarding is also very little. Multiplication, the rewarding could be big. So we need to put our resource investment in the right place, multiplication place. Okay, so that's first consideration. Conclusion, focus more on multiplications. Okay, strategy. How do you focus on the multiplication, the strategy? Yeah, simply reduce the number of multiplication. Is there some way we can use to reduce the number of multiplications? We want to do the same thing, but with fewer number of multiplications. That's our goal. Fewer number of multiplications. Okay, yeah, all right. Now let's do it. Implement the strategy. Here, the implementation, also very important. Although you know the strategy, you know what to do, which direction to go, but you do not have the idea how to implement your strategy. So another important part, implementation, very important. So let's look at this question. How do we implement the strategy? How do you reduce the number of multiplications? Okay. All right. Yeah. So here, the strategy. So we want to reduce this part, number of multiplications. All right. Not the first term, the second term. Okay. All right. All right, yeah, so strategy, direction to go, execution, how to get there. Yeah, now we want to, so we know the direction to go, but we do not know how to get there at this point. How to get there. So we need to explore more information. All right, yeah. How to reduce the number of multiplications. Our new question. For a new question, do we need a new strategy? Yeah. So when we have this new question, we may need a new strategy. Think about it. So we always need some strategy. Okay. Yeah. Here, for implementation, we also need a strategy. Study a simpler case. Yeah. We did that before, right? Fake coin problem, we consider simpler cases, okay? So here, for polynomial, can we study simpler polynomial first, right? Yeah. When we count the multiplications on that general term, we look at some simple cases, right? K equals 1, K equals 2, K equals 3. Then we find the answer. Here, for the polynomial, can we do the same thing here? Polynomial with 2 terms, with 3 terms, and so on. How about that? Simpler cases. Can we try to see if we can reduce the number of multiplications? Yeah. All right, let's do the work. The first case we consider n equals 2. When n equals 2, can we, so here, when n equals 2, can we reduce the number of multiplications? That's what we need to do. We need some new idea to reduce the number of multiplications. When n equals 2, we have a quadratic formula. P sub 2, quadratic formula, 3 terms. A0 plus A1x1 plus A2x2. 3 terms if, think about it. Definitely, in order to reduce the number of multiplication, we need to do computation differently, right? If you use the same computation, you get the same number of multiplication. Doesn't help. So here we want to do different calculation. To do different calculation here, we want to explore property. Okay? What property we can take advantage? So here we look at the last two terms. Can you observe some special property here? The last two terms. What's the property? Any special?
They share an X.
Good, share X. No, that's the property. There is a, can we call common factor? X is the common factor of those two terms. When there is a common factor, what manipulation you can do when you have
On the outside.
yes, factor outside, do factorization, factorize the common factor X. Okay, all right. So here, when we do that, basically we transform the problem. We change the form of the problem. For the value, we do not change, right? We change the form. The value has no change. Same value with different forms. But the result will be different. Because when you change the form, you change the structure. When you change the structure, you have different properties. Then you can take advantage of different properties to get better result. Think about that. Yeah, so this transform step important. Okay, so let's look at how do we change the structure for new outcome. Change structure. Okay, all right. The way to change the structure, do factorization. Okay, yeah. After we factor that common factor X out, we get the right-hand side. X times the parenthesis, inside the parenthesis, X1 plus X2 times X. In this equality, the two sides have the same value, right? We do not change the value, but they have different structure. Mathematical structure are different, right? Two sides. Okay. Left-hand side, when we count the number of multiplications in the left hand, how many multiplications? If we do the calculation using the left-hand side expression. 3, 1 plus 2, 3. But answer that question again. If we count the number of multiplications using the right-hand side expression, how many do we need? 2. That's different, right? Is that number different? Can we say it's a significant reduction? Quite significant, right? 50, not 50%, 33% reduction, right? Let's say, because we use the base 3, all right? Original number is 3. Then we get 1/3 reduction. How about that? 1/3 reduction. So this direction is very promising, right? Encouraging. So we should go along this direction more. Okay? All right. So conclusion, that factorization technique can bring us this gain from 3 multiplications to 2 multiplications. Question. I'm sorry, can you repeat?
I said as you increase the total number of terms, so say we had chosen 7 terms.
Right.
That it becomes less efficient as terms total increases. Factorization.
You say less efficient?
Yeah.
That's efficient. Yeah. All right. Yeah. That question is relatively hard to answer at this point. Because you may not push your technique far enough. The technique is factorization. How far you apply factorization technique, you may not push far enough. If we push it far enough, more efficient. So the next question is, how do we apply this effective technique, factorization technique? Next question. All right. Question. Can we generalize this idea to general M? We have to, yeah, but we need to, answer your question. B.3 Horner's rule. That's the method, smart method we mentioned before, Horner's rule. Okay? Yeah, because this method is important. So there is a name for it, Horner's rule. Okay, let's see what's the rule here. Okay, all right. So here, key to the success, factorization. Okay. So we should push very hard when we apply factorization technique. As hard as we can. In other words, we should use factorization as much as we can. How about that? That's straight. Yeah, scary, yeah. But the effort, the rewarding of the effort is big. Yeah. The strategy for generalization, another strategy. Okay? Yeah, so many strategies. Do factorization as much as we can. Our current strategy. As much as we can. Okay? How about that? Okay? Yeah. We know the reason we can do better factorization. So we should apply as much as we can here. Okay? Here, as much as we can, there is a name for it in algorithm, greedy idea. Greedy algorithm. So this is the greedy idea. So there is a type of algorithms we call greedy algorithms. That's in chapter 8 of the textbook. Very late, chapter 8. Yeah. But I want to bring it here, because for this class, we may not have chance to cover chapter 8. Yeah. But there are a few places we can apply the greedy idea, greedy approach. So this is the first place we can apply that greedy approach. Okay? So when you have some special method, we want to apply it in some sense. In what sense you need to specify? In some sense, as much as we can. That's the greedy approach. Okay? The algorithms, we call it greedy algorithms. Here, we use the greedy algorithms here. Let's do the work. When we do the work, I like to do another experiment where n equals 3. So we do another experiment to get a little more experience. Yeah, because when we have one more term, can we, this time using the greedy strategy to apply factorization, another round, more. All right, yeah, so let's try. Okay. The factorization should cover as many terms as possible. No. So here, we cannot apply factorization on all the terms, right? because there is no common factor for all the terms. All right, but if we ignore the first term, then we have a common factor, right? After we ignore the first term, the remaining three terms, there is a common factor. So we can apply factorization. How about that? So that's the meaning. We apply factorization to cover as many terms as possible. One greedy, so here also the greedy way, okay? Cover as many terms as possible. One greedy definition here, okay? Yeah. Then our first factorization looks like this. So we factor that common factor x out. Inside the parenthesis, there are three terms inside the parenthesis. Tell me, what's the next step? When you see this expression, what do you want to do next? Greedy strategy, do you have another chance to apply factorization inside the parenthesis? Another round factorization. Yeah. After you ignore the first term inside the parenthesis, you have common factor situation. So you can apply factorization another round. Okay. So for the remaining terms, do this factorization, you will get this expression. In this way, we push the factorization as much as we can, right? Very hard to the end. Because after this, we cannot do further factorization. No further factorization can be done. So we have to stop. Okay? That's the best we can do. That's the essence of greedy strategy. Greedy approach, that's the essence of it. Okay? All right. So now we are satisfied with this expression. Question, can we do the same thing for the general n? Our final, our destination, we need to work on the general polynomial with degree n, degree n, to do the same type of factorization. We can, right? Not too hard, right? Using the same pattern here. Using the same pattern here. Push to the general case with the same pattern. Can you see this expression? For the general case. Can you follow that? This is the so-called Horner's rule. If you calculate a polynomial in this way, it looks strange, right? Looks, not normal. Yeah. That's the so-called Horner's rule. Horner's rule. All right. What's the benefit of this way? What is the benefit? Now, I ask you, count the number of multiplications in this last equation. Last polynomial expression. Now you count the number of multiplications and tell me that number. Counting number. Counting number. Can you apply the method I introduced before, counting by reference? Counting by reference. N, that's correct. All right, the first multiplication is here, right? The first multiplication is here. Can you associate with the subscript 1 here? Second multiplication, the parenthesis with the subscript 2, and so on. Okay? Yeah. So this Horner's rule, we apply counting by reference, multiplication, the last one associated with n. You count the subscripts from 1 through m. That's m. Okay? Yeah. Counting by reference. Question? Yeah.
So why wouldn't it be, n plus one?
Yeah. Right. The first one, you do not do multiplication, right? Yeah. Multiplication, when you have a pair of parentheses, you do multiplication, right? But the last multiplication, you do not have pair of parentheses.
I was saying that because it's inside the parentheses.
Right. So here, we associate each multiplication with a subscript number. In that way, subscript number. In that way,
What's the third one?
right, third one, x inside that, x3 plus something. Yeah. Now you should appreciate the counting by reference, right? Yeah. Because this one is harder. If you do not do that one-to-one correspondence, one-to-one association, it would be hard, right? Not that straightforward. But if you discover that one-to-one correspondence relationship, it's not hard. Not that hard. Okay, all right. Yeah, I hope you get it. And multiplications. Now we need to see how good is our new algorithm. This is a new algorithm, Horner's rule. The number of additions the same, still n, right? We do not reduce the number of additions, but we reduce the number of multiplications. Okay, yeah. So let's look, yeah. Yeah, we have that, and yeah. So we need to do the last round analysis to see how big is the improvement. How big is the improvement? We want to see that. Is that improvement big or little? We want to see, we want to get some impression of that. Okay, yeah. Multiplication reduction. Let's see the multiplication reduction from the number. So here, let's consider the number of multiplication, that reduction. Okay, now. Older method, this many, 1/2 times n plus 1. Old method. Horner's rule, new method, n. This reduction. Can you see? Definitely you can see the difference, but how big is the difference? Can you see that? How big is the difference? Can we say that's a big improvement? Big improvement? Super big improvement? Yeah.
It's like about 50% improvement, right?
I mean, so it's an exponential one, right? Like the more ends you have, the bigger the difference.
Good. But he said 50%. He said something 50%. Is that a fair number, fair description? Only 50? Only 50 improvement? Can we say 99% improvement? Is it a fair number? 99% improvement? How do you feel? Do you think, you know, so we want to see how good is the improvement. Can we say we comfortably get 99% improvement? If it's a fair statement or not, 99% improvement.
But you got a certain point, I feel it's probably gonna be a 99, depending on how big n is.
Yes, Yeah, how big n is. When n is small, we don't have 99%, right?
Right.
When n is large, do we have, when n is very large, do we have, n is very large, do we have 99% improvement?
Yeah, I mean, like, when we were looking at the
Yeah.
work for like polynomial like 3, it was already a 50%. Because the original took 6 multiplications, and the new one's 3.
For our algorithm, so we only worry about large n. We do not worry about small n. So the concern always when n is very large. That's our concern. When n is relatively small, we don't worry. Our computer is super fast. So we never worry about when n is small. Only when n is very large, then we really need to see how well our algorithm performs. Okay, so you can assume, let's say when n is sufficiently large, can we say that? When n is sufficiently large, we have improvement at least 99%. Is that a fair statement? Actually, it's a modest, too modest. 99 is not big enough, too modest. Too modest. Not strong enough. Not strong enough. All right? Yeah. In order to convince you, yeah, here, I want to convince you. How big is the improvement here? Our last 10 minutes, we have final 10 minutes. I want to convince you how big is the improvement. Okay, bigger than that, 99%. When n is sufficiently large, there is this. Yes. All right. Let's see. Let's do some experiments to see that difference. All right. Impact of multiplication reduction. This is the reduction, but we need to plug in some numbers to see the impact. All right. How do we visualize the improvement? We want to feel about, visualize. Because when we look at these formulas, it's hard to visualize, right? In our mind, how do you visualize these two different formulas? You cannot. But if we change to some concrete quantities, then you can visualize easily. Here, I want to convert it to some easy quantities in your mind, so you can feel about those quantities. I know how big they are, so you can get an idea. Span, yeah, but I need to, yeah, put in the airplane, but only 10 minutes. Yeah, I hope. Yeah. Let me just, yeah, all right. Yeah, visualization, okay? The last step, visualization. Let's work on some examples. Let's plug in two special n values here. Okay, the first one, n equals 1,000. Can we say sufficiently large here? N equals 1,000. Yeah, very large, but think about we're in a big data era. Okay, big data era, that 1,000 data items, not that big. People talk about millions, billions data items. That 1,000, very small number. Okay, yeah, let's, our first example, we work on this relatively small number. N, all right? Yeah, plug in, right-hand side, just 1,000. What is the left-hand side? I use approximation. In may not be precise, okay? Yeah, approximation, yeah. All right, 500,000. 500,000 versus 1,000. 500 to 1 ratio. Think about 500 to 1 ratio. Is it better than 99%? Think about that. It's better than 99%, right? Much better.
feel like you reached 99% around like 135.
Yes. Yeah, so that's why I say, too modest. But you may, at the beginning, you may feel I'm too aggressive, right? Yeah, the estimate, too aggressive. Yeah. All right, second, let's try second, this time 1 million. N equals 1 million. All right, so this time, right-hand side, 1 million. How big is the left-hand side? Plug in, still approximation. How big is this number? Can you read that number using appropriate?
Half a trillion.
500 billion. 500.
Trillion?
Half a trillion.
Half a trillion. Yeah. He said half a trillion. All right. Yeah. Here. So million, billion. So 500 billion. Yeah. Half a trillion. Good. Half a trillion. Half 1,000 billion, because 1,000 billion, that's trillion. Half 1,000 billion, 500 billion. Yeah. The ratio, let's look at the ratio here. 500,000 to 1 ratio. 500,000 to 1 ratio. All right? Yeah. Now you believe the difference is huge, right? The difference is huge. Not, but you didn't realize we are in the big data era. All right? Big data era. So you can imagine the amount of data we may need to handle every day. Okay? Yes. So many big servers in the world, cloud computing, you can imagine. All right? Yeah. Then the last piece of the story, the final 5 minutes, I still push another step forward. Last piece. All right. We need to get a concrete impression here. I want to give you another story piece, concrete expression. Suppose we run these two different algorithms on the same machine in a real world situation, right? So you provide business solutions to your customers, okay? Suppose you have two different solutions. Old one, the first one, you get a response time corresponding this 500,000 time units. Then the improved one later, so you try very hard, you find a much better solution, and the response time is 1 time unit. Okay, now you solve the same problem. Here, let's just assume 1 time unit corresponds to 1 second. How about that? 1 second, you know how fast it is, right? So when you use the new method, you hit the enter after 1 second, your customer can see the result. That's the second method. 1 second after you hit the enter, result on screen. Okay, yeah. Think about how happy your customer are, all right? Yeah. Now, let's look at the first method. After hit the hand, enter. How long your customers need to wait? We use second time unit. 1 time unit is the second. Okay, all right. Then you need to wait 500,000 seconds. How long is that? Let's do the conversion. How many days? How many hours? Let's convert to that number. Okay, 5.8 days. If you do conversion, you'll get 5.8 days. Close to 6 days. Think about that.
Go on vacation.
Yeah, think about you bring the solution to your customers. Well, you hit the button. your customer, they need to wait for 5.8 days. Think about that. Right? Can you imagine that? But the second solution, I think the first one, you won't bring the solution to customers, right? So you don't want to embarrass yourself, right? But the second one, you will be very happy to bring that solution, right? The second solution, think about that. You're very happy. 1 second. Okay? Yeah. So through this example, I try to let you feel for this class, after we learn all the knowledge, all the techniques, we have a chance to do this big improvement. Okay? Yeah. Ordinary way, the slow, but use some smart way, we can get this big improvement. All right. So that's the part B. We have part C, part D, but that's relatively short. So we will complete that next time. Part C, part D. Next time. Okay?